Hi, Ahmed. Hi, everyone.
Hello, Animash. Hello, everyone.
I hope everyone is doing good. And today we have Ahmed, and we'll be discussing about eBPF in a service mesh. So, something about Ahmed is a chief software architecture and engineer and has more than 2 decades of experience in designing, implementing, and delivering software systems using Agile and DevOps practices. He's also a consultant. And over to you. I know I'm not justified your introduction, so feel free to introduce yourself to the audience.
No, that's great. Thank you very much, Animash, and thank you for having me today. A warm welcome to all our viewers. So, today I'll be talking about eBPF, the next big thing in Service Mesh. So, before we start talking about eBPF, let me further introduce myself in addition to what my friend Animash has already said. So, my name is Ahmed Misbah. I am founder of Tech Cafe, which is a technical podcast dedicated to empowering the tech community and encouraging innovation in the tech industry. I'm a chief software architect, a coach, and an instructor. I'm also a speaker at multiple events, including the DevOps Days Cairo conference, the Software Engineering Competence Center, the Africa and Middle East Conference on Software Engineering, the Google Developer Group, Orange DevTest Days, and Delta Technopreneurs. Being founder of Tech Cafe, I would like to invite you all to visit Tech Cafe, either by scanning the QR or just typing techcafe.com to see our previous episodes on the podcast and to learn more about our professional services, which include technical consulting and technical workshops and training. Please also follow us on LinkedIn. We are very active there, and if you follow LinkedIn, you'll be able to receive our latest updates. So, what are the topics of interest, my topics of interest? So, I like speaking about software architecture, cloud native architectures and beyond. And I think today's topic is part of cloud native architectures, free and open source software, agile, lean, and DevOps, and artificial intelligence and machine learning. As my friend Animesh has said, I have 2 decades of software development experience. I've delivered 2 award-winning innovative solutions, winner of the Dell Hacktrick 2022 UI UX track. I'm a PhD candidate, currently preparing a thesis and research in Arabic large language models in a specific NLP task. And I have a master's degree in machine learning and many other professional certifications. So without further ado, let's get started. I'll start first with describing our agenda. So since we are going to be talking about Service Mesh, we need to first introduce Service Mesh and basically explain what it is. Then we're going to be talking about the problem with the most common service mesh implementation, and that is the sidecar-based implementation. And once we have described the problem very clearly, we're going to talk about a proposed solution using eBPF and eBPF-based service mesh. So we'll need first to explain what eBPF is. Then we'll talk about eBPF-based service mesh implementations. Of course, it's not all sunshine and roses. Everything comes with its set of limitations. So we'll talk about the limitations of eBPF-based service mesh implementations. And then we're going to be talking about the current technologies that are available for those of you who will be interested in using this very interesting technology when implementing service mesh. So let's get right to it. Let's first talk about what service mesh is. So service mesh is a dedicated communication layer for facilitating service-to-service communications between services, and between brackets I included micro services, using a proxy, often a sidecar proxy or the ambassador pattern. Now, having such a dedicated communication layer can provide several benefits. Those include observability into communications, traffic management, secure connections between the services using mutual TLS, automating retries and backup for failed requests, and this in return improves your resilience. Many deployment strategies, including canary releases, blue-green deployments, etc. And last but not least, separating the business logic of the application from all of the previous tasks that we have described previously. So this is what service mesh is, and these are the benefits that service mesh provides to you when you are using a service-based architecture or some sort of distributed architectural style. This diagram over here explains the high-level architecture of a service mesh implementation. So you've got a control plane, which includes all of the components of the service mesh's control plane. Then you have the data plane, which will have your nodes, basically, and the corresponding pods running within each node. And of course, I'm using Kubernetes terminology here. And with every pod, you basically have your main container, your applications container, and another container for your sidecar proxy. And your sidecar proxy allows you to have all of the features we have spoken about previously in the previous slide. And then you've got a lot of the data that are being captured by the sidecar proxy being transferred to components in the control plane, so that these components in return will share the data with other tools for distributed tracing or monitoring, etc., so that software developers or even operations engineers can make use of this data. Okay. So we've described what service mesh is, and we said that one of its common implementations is using a sidecar, and we've shown how a sidecar used in the previous diagram. Now, let's talk about the problems with sidecar-based implementations. So as we've described in the previous slide, so a sidecar is basically another container that you deploy with the main container that hosts your primary application, and adds a number of features, including observability, traffic management, security, etc. And yeah, it's a sidecar is originally something that was in motorcycles. So if you see the picture in front of you right now, you've got the motorcycle, which is the main vehicle, and then you have the sidecar attached to it in order to have another passenger on board, or perhaps carry luggage or whatever. And this sidecar is attached to the main vehicle, which is the motorcycle. So this is what a sidecar is. Its origins, if that's the right term to use. So in the software, the sidecar pattern is pretty much the same. If you're using Kubernetes and you're deploying your applications in pods, and this pod is going to include a container, it's going to include another container for the sidecar proxy. And basically, all the traffic going back and forth of your primary application has to go through this sidecar proxy first in order to be able to provide you with whatever features that your service mesh implementation provides. So yeah, this is basically the sidecar pattern. It involves attaching an auxiliary container to the main application container within the same pod. This auxiliary container shares the same lifecycle and network namespace as the main container. The sidecar container's purpose is to provide additional functionalities, services, or capabilities to the main container without tightly coupling them. And this was the benefit that we talked about a couple of slides back, okay, is that your primary application will be mainly focused on your core functionality, and the sidecar proxy will add additional functionalities, but there's going to be this separation of concerns, which is a software design principle that we want to promote. In an article published on Medium in 2020, Paul Klinker ran a benchmark on an application that uses only Docker, uses Kubernetes, and uses Kubernetes with EC2 in order to measure the response time of each deployment or each configuration. He ran the experiment first on his local machine, and then he ran a similar experiment on AWS, but using Red Hat OpenShift container platform instead of raw Kubernetes. So, and the title of that article was Performance Impacts of an EC2 Service Mesh. He got some very interesting results, and you can see these results in front of you on the bar chart. And these results suggest that every time you deploy your application on a platform that basically adds more functionality, or perhaps more layers of abstraction, you tend to have a penalty. And that penalty is basically added latency to your application, which means that the response time of your application rises. And yeah, we can see from the bar chart here, going from Docker to Kubernetes adds latency, from Kubernetes to Kubernetes with EC2 adds latency, and then using EC2 with mutual TLS, it's pretty much the same on a local deployment or local configuration. Okay, but it's still more than just using Kubernetes without EC2 and using just containers without a container orchestration platform. As I've said previously, he ran a similar experiment, but this time on an OpenShift container platform. I think that's version 4.4, running on AWS. So basically running on a public cloud. And he first ran his pods on OpenShift without EC2, then using EC2, then using EC2 with sorry, so using EC2 with mutual TLS. And those were the results that he got. So the response times here are much larger than the previous experiment. And this may be due to a number of factors. This includes the added latency of having the deployment on the cloud instead of being on a local machine. But we can see very clearly that when you have EC2, you have added latency, and when you have EC2 with mutual TLS enabled, you have more added latency. Now, this diagram over here explains the cost of sidecar injection. And that's because your application's traffic basically has to go through the Service Mesh proxy. And yeah, it has to go through your OCI stack for every container that you have. So leaving your application, it has to go through its OCI stack, then going through the Service Mesh, ingress and egress has to go again through its OSI stack. And this is what basically adds latency. And latency is something that many developers tend to forget. And they get surprised later on of why their application is not performing the way it should. So the diagram over here explains the 8 fallacies of distributed systems. And we can see that one of them is the wrong assumption that latency is 0. No, latency is never 0. And your latency may increase or decrease depending on your system design and depending on the technologies that you're using as well. So yeah, we have to understand that everything comes at a price. And if you're going to be using sidecars, these injected sidecars are going to be adding latency to your application. Now, in this diagram, we've seen something here that is very interesting, and that is the kernel. So can't we move from a sidecar model to a kernel model? Can't we move the Service Mesh implementation, instead of it being a sidecar that you attach as a container within your application's pod, can't we move that to the operating system kernel? Because getting data from network traffic is something that you can do on the kernel. So can't we do something like that? The answer is yes. And this is where eBPF comes in. So enter eBPF. eBPF abbreviation, eBPF is abbreviation for Extended Berkeley Packet Filter. This is a revolutionary technology with origins in the Linux kernel that can run sandboxed programs in a privileged context, such as the operating system kernel. So everybody is thinking right now, yeah, so this is the technology that is going to allow us to, instead of using sidecars, that we implement whatever functionality that existed in the sidecar in a program that would actually run within the operating system kernel. Yes, if this is what you had in mind, that is exactly what eBPF is. So it is used to safely and efficiently extend the capabilities of the kernel without requiring to change kernel source code or load kernel modules. So historically, the operating system has always been an ideal place to implement observability, security, and network functionality due to the kernel's privileged ability to oversee and control the entire system. But at the same time, an operating system kernel is hard to evolve due to its central role and high requirement towards stability and security. The rate of innovation at the operating system level has thus traditionally been lower compared to functionality implemented outside of the operating system. So eBPF comes in to change this formula fundamentally by allowing you to run sandbox programs within the operating system. Application developers can run eBPF programs to add additional capabilities to the operating system at runtime. The operating system then guarantees safety and execution efficiency as if natively compiled with the aid of just-in-time compiler and verification engine. This has led to a wave of eBPF-based projects covering a wide array of use cases, including the Sevice Mesh use case. This includes next-generation networking as well, observability, and security functionality. So this is kind of a high-level architecture of how eBPF looks like. So you've got your programs typically running in your user space, and then you've got other programs that run within the kernel and that provide functionality to programs running within the user space, depending on their use cases. So you can have use cases that are related to your storage device, for example. You can have use cases that are related to your network device or network interface. And that is the scope of Sevice Mesh. So basically, this is how typically eBPF implementations look like. Okay, you've got the layer of eBPF projects, which provide a kind of abstractions that allow you to implement eBPF use cases. You've got the eBPF SDKs implemented using one of the programming languages you see in front of you. Then you've got the kernel space, which runs the verification, the just-in-time compilation, and basically runs your eBPF program. And your eBPF project interacts with this program in order to get the different functionalities that it requires. And here is an example. So on the left, you've got an example of eBPF being implemented for a use case that is in the domain of storage. And on the right, you've got an example of an implementation for a use case like Service Mesh that is basically related to your network device. So let's explain how eBPF works in a little bit more details. So in a lot of scenarios, eBPF is not used directly, but indirectly via projects like Cilium, BCC, BPF trace, etc., which provide an abstraction on top of eBPF and does not require to write programs directly, but instead offer the ability to specify intent-based definitions, which are then implemented with eBPF. If no higher level abstraction exists, then you need to write your programs directly. The Linux kernel expects eBPF programs to be loaded in the form of bytecode. So what happens next is that when the desired hook has been identified, the eBPF program can be loaded into the Linux kernel using the BPF system call. This is typically done using one of the available eBPF libraries. As the program is loaded into the Linux kernel, it passes through 2 steps before being attached to the requested hook. These verification steps ensure that the eBPF program is safe to run, and it validates that the program meets several conditions. So after that is done, and you have a running eBPF program within your Linux kernel, a vital aspect of the eBPF programs is the ability to share collected information and to store state. For this purpose, eBPF programs can leverage the concept of eBPF maps to store and retrieve data in a wide set of data structures. eBPF maps can be accessed from eBPF programs as well as from applications in the user space via a system call. So this is basically the life cycle of a typical eBPF program. And for Service Mesh, it works pretty much the same. You've got an eBPF program, which has all of the tasks of a Service Mesh implemented into it, like Layer 7 traffic management, authentication, authorization, tracing and observability, resilience and reliability. And this runs within the kernel. And it basically is a replacement for the sidecar-based implementation. Now, remember the benchmark that we have spoken about earlier with the sidecar-based implementation in 2020. Here's another benchmark that was run by Thomas Graf in 2021, but this time using eBPF-based implementation. So as you can see, there is a big difference in latency between an eBPF-based implementation and a proxy-based implementation. Now, in this benchmark you see in front of you, the setup is running a steady 10K HTTP requests per second over a fixed number of connections between 2 pods running on 2 different nodes. and measures the mean latency for these requests. So you can see the big difference between both implementations. The very, very low latency that you achieve with eBPF-based service mesh implementations. Okay, so now that you understand how eBPF works, and now that you've seen its benefits being used in service mesh, let's talk about its implementations. So for any eBPF code to run, it will only run on the kernel when the kernel decisively proves that it's safe. Now, in order for the kernel to guarantee the safety of the program, you have some limitations. eBPF programs are not allowed to block. They're not allowed to have unbounded loops. They're not allowed to exceed a certain maximum size. And the verifier must be able to evaluate all possible paths of execution. Okay, so yeah, eBPF has made evolving the kernel much easier than it was in the past, but still programming the kernel has its limitation, because the kernel is not a place that you want to go unstable. So yeah, you still have these limitations with eBPF in general, and those are inherent in service mesh. So with these limitations in mind, this means that the full scope of service mesh features are far outside of the realm of technical feasibility with an eBPF only approach. And you can see in front of you now a list of items in the service mesh scope that do face some limitations with eBPF based implementations. So because of these technical limitations, the idea of a pure eBPF service mesh is a non-starter. So what? This is it. We will just have a half-baked service mesh implementation with BPF. No, there's actually a solution for that. And this is what we call an eBPF accelerated pair node proxy. So when specific use cases in service mesh cannot be implemented with an eBPF only approach, the mesh can fall back onto a pair node proxy model that directly integrates the proxy with the socket layer of the kernel. So people are going to start wondering right now, another proxy? Wasn't that the thing that eBPF-based implementations replaced? Well, you're right and wrong. Yeah, it is still a proxy, indeed, but with sidecar-based implementations, you had a proxy pair application. But with this pair node proxy implementation, you have a proxy pair node instead of pair application. So with that, you have easier manageability, etc. So instead of having 30 proxies for 30 pods, now you have one proxy per node and not per pod. And this is very close to ambient mesh architecture. There is another kind of architecture that tries to solve the problems with sidecar-based implementations. This is called the ambient mesh. And yeah, it is based on the same concept, pair node proxy, but not exactly. You've got not just one node, but I think two nodes running. But this is another topic that we can talk about in another session. Sorry. So lastly, let's talk about service-based eBPF-based service mesh technologies. So yeah, Cilium. Sorry for that. So yeah, let's talk about Cilium service mesh. So Cilium is a eBPF-based implementation for service mesh. It provides you with the typical tasks that should be provided by a service mesh, and it also uses the pair node proxy implementation in order to implement the use cases that cannot be implemented using eBPF. And to prove that this kind of technology is now getting really serious attention, Cisco at the end of 2023 announced its intention to acquire Isovalent, the company behind the Cilium open source project, which shows that the big players in the market are starting to see the benefit of eBPF-based service mesh. So this is the high-level architecture of Cilium's sidecarless model versus the traditional sidecar-based model. So yeah, we see less of the socket TCP/IP Ethernet stack, and this in turn will result in reduced latency, which is what you want with such an implementation. Now, we've mentioned that Cilium offers your typical service mesh functionalities. Those include level 7 traffic management and load balancing, TLS termination, canary rollouts, retries, rate limiting, circuit breaking, etc., configured through Envoy, tracing with OpenTelemetry and Jaeger integration, and built-in Kubernetes ingress support. But is this the only technology available in the eBPF service mesh landscape? Of course not. You have many other technologies, and you can scan the QR in front of you right now, or basically type in the URL below, eBPF.io/applications, to check out the many other implementations of eBPF in service mesh and in other use cases. So yeah, that's it. Thank you very much for remaining that long, and I hope you found this session informative and useful. And yeah, feel free to reach out to me by scanning this QR. This includes a link to my personal website and my social media links and my email. So if you have any questions, please feel free to reach out to me and ask. And again, I thank Animesh for having me today. And yeah, thanks a lot.
Thank you, Ahmed. It was a very wonderful and great session. I definitely got to learn more about how the eBPF works at the base level, and especially the Cisco news. That's an exciting to see, like how it's gonna evolve with Cilium and Isovalent together with the Cisco, because Cisco has been in the network game for a very long time. That's something that they have a great standards as well. So let's see how where it goes and how it goes. And once again, thank you for sparing the time to join in and share your insights with us.
The pleasure is all mine, Amish. Thank you very much, Animesh.
Thank you, everyone. So I'll have all the links in the chat as well in the comment section. You can take up from here, and feel free to connect with Ahmed if you have any questions regarding eBPF or how it works in the service mesh. Thank you, everyone. Thank you for joining.
Thank you. Bye bye.